There's only one reaction of alkanes that's in any way meaningful for us besides combustion. So as organic chemists, we want to be able to control our reactions, and combustion is a controllable reaction in many ways, but you can't really control the products. You're always going to make carbon dioxide and water. Carbon dioxide is no longer an organic compound, so that reaction is not very helpful for us as organic chemists. But free radical halogenation is helpful. Free radical halogenation gives you a compound called a halogenoalkane. And in this little lesson, we're going to learn how that happens. So just to give you an overview then, in free radical halogenation, you're really only talking about chlorine or bromine for all practical purposes. And what's required is ultraviolet light or a lot of heat. And what the overall reaction is that you'll get your halogen reacting with whatever your alkane is. I just use the simplest one here, methane, to make a halogenated methane. So a methane that essentially has had a chlorine added to it and a hydrogen removed to it. That hydrogen then very easily could react with the chlorine to form a hydrogen chloride. So if we're taking a look at it here, what's going on in this particular drawing or this particular picture is in the beginning there's bromine that's been added to hexane. So bromine can be dissolved in water, but it doesn't dissolve very well. It dissolves much more readily in hexane, which is why the hexane is a darker red color. And then the UV light's turned on. So after the UV light is turned on, bromine will slowly react with the hexane. And as it's reacting with the hexane, the color goes away because bromine, being red in color, is gone. It's reacted. And the elemental bromine is in lower concentration, less red color, and now it's reacted to form some sort of brominated hexane molecule. And we'll talk about what kind of molecules you can form in a second here. So as we said, ultraviolet light is used to cleave the bond between the halogens, either bromine or chlorine. And when that happens, the kind of cleavage, it's called the breakage of the bond, is called homolytic cleavage. Cleavage just means breakage, and homolytic just means that it's the same on each side. So what we have when we have homolytic cleavage is we have one electron from that bond going to this chlorine, and the other electron from that bond going to the chlorine on the right. Now, what I want to show you here is how we're going to show mechanisms in this class. So if you see an arrow with one electron, or with one head on it, that means that you have one electron. When you're making what's called a mechanism, you're showing what happens. If you see an arrow with two heads, that means you have a pair of electrons that's moving. So in this case, we have one electron going to one chlorine, one electron going to the other chlorine, and what do we have as a result of that? We have the chlorine on the left with a structure that looks like this, the chlorine on the right with a structure that looks like this. Essentially, we have atomic chlorine, and we have two of them. So you'll see it written this way, or you may also see it written this way. Okay, so that's the first step of this process. So now what we do is we have two chlorine atoms in this process, and they have unpaired electrons. Species with unpaired electrons are called radicals. So this you could also call the chlorine radical. And all that means is that as a molecule, it has one unpaired electron. We're coding this to make it easier for you to see what's going on here, but of course the four hydrogens on the carbon and methane are the same. Now, we've just generated a chlorine radical. That chlorine radical has one unpaired electron, and unpaired electrons in general are very reactive. So any species with an unpaired electron is considered a radical, and radicals are very reactive, and that's the case here for this chlorine radical. So this chlorine radical is extraordinarily reactive, and as it gets close to methane, what it can do is it's going to donate this electron to form a bond. So this one electron is going to come over here, and from methane, one of these electrons is going to come over here. Now, so what's going on now is there's a bond forming between this H and the Cl, but only one of the electrons went to that bond. Only one of the electrons from the bond between carbon and hydrogen went to the bond. The other electron stays here. So what do we get? As a result of that reaction, we have chlorine. I'm going to sort of draw this very specifically here. Bonded to hydrogen. And the way I'm drawing this is just that bond indicates that one of the electrons came from chlorine, one of the electrons came from the electrons that were between carbon and hydrogen before. Now what do we have over here remaining? We have the methyl radical. So remember just a second ago we had a chlorine radical, now we have a methyl radical. And that is where we talk about propagation. We've propagated the radical. We've had a chemical reaction, but we've propagated a new radical. Now that methyl radical itself is very, very reactive. So what happens? It reacts. So what we're going to show next is what that reaction looks like. Here we have a methyl radical that we've just generated, and it's going to maybe encounter another chlorine molecule. The same exact process can occur where the methyl radical will donate an electron, and a chlorine atom from the chlorine molecule will donate an electron. The other electron will go to this chlorine here. So what are we left with? Let's draw it. We have hydrogen bound to carbon, hydrogen bound to carbon, hydrogen bound to carbon. And again, I'm just showing the coloring here just to show where the electrons are coming from. So that new bond that we've made has one electron coming from carbon, one electron coming from chlorine. And then after that, we have a chlorine radical again. So once you've initiated this reaction, it keeps on going. You have radical formation after radical formation after radical formation after radical formation until you reach the next step. So over time, what's going to happen is free radical halogenation is going to generate more and more and more radicals. And as you're generating more and more radicals, the probability of two radicals coming in contact with one another increases. So let's imagine for a second that we have a chlorine radical coming in contact with a chlorine radical. In this case, both of them are very reactive. This chlorine radical will donate its electron, and this chlorine radical will donate its unpaired electron to make chlorine again. So now we've terminated the process of the reaction. So this is the last step, sort of the ending step of this whole process called termination. So termination occurs anytime you have two free radicals coming in contact with one another. It doesn't just have to be chlorine and chlorine. You could have had a methyl radical come in contact with a methyl radical. That's possible as well. Now, when a methyl radical comes in contact with a methyl radical, though, of course, you're not going to just be making a chlorinated alkane anymore. This time you're going to make a new compound. That occurs fairly rarely, but it does occur. So if you would actually do some analysis and see what's in your pot at the end where you're making this reaction occur, you wouldn't find much ethane, but you would find some. So that's the process of free radical halogenation. So 3 steps: propagation, which is initiated with ultraviolet light or heat, and then you have propagation, which is when one radical reacts with a molecule that is not a radical to form a non-radical molecule and then a new radical. And then finally termination, where two radicals come in contact with one another. You may be asking yourself at this point, well, why would I even go through the process of doing this if I'm an organic chemist? And really, for alkanes, they're very, very plentiful. We can get them out of the ground in terms of finding fossil fuels. But except for combustion, there aren't really many meaningful reactions that we can perform with alkanes. But we can make halogenoalkanes, which is what we just made. We made chloromethane. And chloromethane and other halogenoalkanes are very useful. They can be industrially useful because they can use this as a starting point to make other materials. if you think about it, the C to H bond in alkanes is not very interesting because it's not very polar. But as soon as you put a chlorine or a bromine attached to a C, now you have a difference in electronegativity. You have a weaker bond, and that bond now can be used to as a starting point for other chemical reactions. We'll learn those other chemical reactions soon, but that's why we do it. Now, when we look at alkanes, there's one piece of vocabulary I want to be able to talk to you about, and that is carbons being primary, secondary, or tertiary. So a carbon is considered to be primary if it's at the end of the chain. Okay, so any carbon at the end of the chain is called a primary carbon. And if I would make the challenge for you to identify all the primary carbons, I think we can do that. So a primary carbon is essentially something that's at the end of a chain, so it has to be bound to 3 other hydrogens. So let's find all the ones that are bound to 3 other hydrogens. I see one here, I see one here, I see one here, and here, and here. Okay, so these are primary. And sometimes you'll see that written with a first degree or a 1 degree. Okay. The next kind of carbon that we would be interested in knowing about is something called a secondary carbon. A secondary carbon is a carbon that's not at the end of the chain. It's attached to 2 other carbons. So if I take a look at this case here, if I'm trying to find the carbons that are attached to 2 other carbons, the secondary carbons, I see one here, the middle carbon in propane, and I see one here, that's carbon right there on methyl butane. So that's a carbon that's attached to 2 other carbons. That's called a secondary carbon. Finally, we have carbons that are attached to 3 other carbons. They're called tertiary carbons. So tertiary carbons, if we're taking a look in this particular molecule, I'm trying to find them, and I see that there's only one, and it's this one right here. So here's a tertiary carbon. It's attached to a 1, 2, 3 carbons, so that's a tertiary carbon. Now, in terms of free radical halogenation, being tertiary, primary, or secondary actually really matters. So free radicals form more easily when that radical can be stabilized by withdrawing electrons from neighboring atoms. Carbon has more electrons to it than hydrogen does. So tertiary radicals are pretty stable because that radical, a tertiary radical, can draw electrons in from those bonds to sort of what we call stabilize the radical. So tertiary radicals are the most stable. And if they're the most stable, that means that they can actually stick around or react. So when you do free radical halogenation, the kinds of carbons that react most easily are tertiary carbons. The ones that react least easily are primary carbons because as a radical, these are least stable. I'm going to make a quick note here just so we don't forget that. As radicals, these are least stable. So if they're less stable as radicals, they can actually just sort of go in the reverse reaction instead of just going forward and making that reaction occur. So that's just something to be aware of. We're going to take a look at a sort of sample problem in the next slide. So here we have chlorine reacting with propane, and we could make 2 possible products. We could make 1 chloropropane, or you can make 2 chloropropane. So, and if you're just looking at it in terms like, well, where could it actually go? Well, over here, 1 chloropropane, that could occur if that chlorine happens to react here, or here, or here, or here, or here, or here. 2 chloropropane can only form if it reacts here or here. Still, even with having 6 hydrogens for a chlorine to react with versus 2 hydrogens, the primary product of this reaction is 2 chloropropane. Why? Because when this radical forms, this radical right here, carbon with its extra electrons can sort of have some of those extra electrons, not extra electrons, but like the 6 electrons that make up carbon. Those 6 electrons can go and stabilize the radical. That radical is pulling electrons towards it, and it stabilizes the carbon. So this is the radical that is the most stable. Okay, the primary carbon as a radical is not very stable because there's one fewer carbon for the terminal carbon to pull electrons from. So I guess the take-home message for this is that when you do free radical halogenation, just look for it's best to put the halogen on the highest order carbon. So that sort of wraps up our reactions of alkanes. They can either be combusted or they can undergo free radical halogenation. Next, there's going to be a little bit of a note sheet. I want you to try to fill out that note sheet, and then we're going to work on taking a formative next class.